My name is Andrew Kaminsky. I am the manager of the Aerospace Data Science Group at CFD Research Corporation. In this presentation, I will be discussing our Phase 2 SBIR effort with the Navy Strategic Systems Program, in which we are developing a digital engineering framework for seeker model evaluation in hypersonic environments. Thank you for your attention. Before diving into our technology, I would like to provide a quick introduction to our company. CFD Research Corporation is a small business with headquarters in Huntsville, Alabama, and offices in Dayton, Ohio, and Fort Walton, Florida. We also have experimental test facilities in Hollywood, Alabama. CFD Research Corporation has a staff of 230 employees, 70% of which hold advanced degrees. With these subject matter experts, our company focuses on performing cutting-edge research. We have capabilities spanning from modeling and simulation, design and prototyping software development, and test and evaluation. Our company has transitioned several technologies to market, and we have spun out 6 companies to date. We hold 80 patents, with 40 of these patents being actively licensed. Our company also has successfully transitioned battery, weather modeling, machine learning, and design optimization software through the SBIR program, with each of these technologies supporting DoD programs under Phase 3 SBIR efforts. Our DoD SBIR Commercialization Achievement Index puts us in the top 10% of companies nationwide. Moving to the work of the present SBIR effort, we will begin by describing the underlying motivation for the work. The motivation for this effort was the desire for a robust seeker modeling capability that can be used to perform research involving fundamental design trade-offs for future radar concepts, as well as efficiently predicting operational performance of those radar seeker subsystems. Seeker models are needed at all stages of the weapon development process. To support DoD acquisition, models need to be continually refined as additional simulation and experimental data collection is performed. This desire is highlighted by the push towards developing digital twins, which follow a concept from inception through operational deployment. For best use, these models need to capture all the relevant multiphysics and enable performance assessment at the system level. Computational electromagnetic modeling is critical to the design of seeker subsystems. The current state of practice often simplifies the seeker design process by neglecting the full set of multiphysics and limiting design to system-level objectives. Our framework is developed to improve the state of practice on both of these fronts. Aerothermal and thermoelastic impacts of the hypersonic environment affect radar measurement accuracy. Our tool models the impact of aerodynamic heating for specific radome and antenna placements and deformation of exotic airframes to inform design. Specifically, we capture the in-depth heating, static deformation, and modal dynamics of the structure and their impact on the seeker pattern. The second key improvement is the ability to deploy these multiphysics models in a form that runs rapidly enough to be integrated as a subsystem of a full system in a mission-level model. By providing fast evaluation through machine learning models, seekers can be assessed for mission-specific performance. This performance can then be used to inform design trades and ultimately provide a high-fidelity design-level modeling environment for radar seeker subsystems that captures the relevant operational and environmental constraints of hypersonic flight for end-to-end integrated performance evaluation. To address these challenges and supply these improvements, we developed a framework we call HyDetector. That is, the Hypersonic Digital Engineering Testbed for evaluating concept radars. HyDetector allows us to build models of vehicle and radar seeker subsystems. These models characterize the antenna or seeker performance for different conditions. We then encode this characterization in a fast-running form using machine learning. The machine learning model allows us to input a condition and provide the antenna signal strength at rates exceeding 1,000 Hz. This model can then be deployed within mission-level modeling tools like AFSIM or CWS to assess the performance of the design at the system level and evaluating it for specific missions of interest. Using this information, we can then update the design material, location, or size and iterate towards improved seeker designs. As of August 2023, we are 6 months into our SBR Phase 2 base. Significant development was performed during our Phase 1 base and option period and the first third of our Phase 2. In the Phase 1, we developed our software architecture. We performed verification studies of our individual tools for modeling the aerothermal, thermoelastic, and electromagnetic effects using results from the literature. Following individual component verification, we integrated the modeling and simulation tools and containerized them for easier deployment. We demonstrated our integration using a patch antenna onboard a generic hypersonic vehicle with a prescribed trajectory. In the Phase 2, thus far, we have stood up our surrogate modeling capability. We've demonstrated the ability of the surrogate model to capture the thermal response and deformation of our vehicle to within a few percent in a form that can be evaluated at rates of thousands of hertz. Our next steps are to demonstrate the deployment of our model within mission modeling tools to assess the antenna design quality. Then we will use this information to feed a design loop. The capability will be demonstrated for a candidate radar system identified in collaboration with the Navy. And then in the Phase 2 option, we will work to transition our software framework through training and beta testing. The key features of our high detector framework are fourfold. First, we have developed a standardized software architecture. This allows us to easily integrate modeling and simulation tools with machine learning techniques using common interfaces and data types. Next, and perhaps most critically, we provide a workflow for capturing the full set of multiphysics impacting our onboard seeker subsystem. The aerothermal and thermoelastic response is captured and then utilized by electromagnetic modeling tools to improve our understanding of the antenna performance in hypersonic environments. Third, we utilize surrogate modeling to convert the capability models to a form that can be evaluated rapidly. This allows us to deploy the seeker models as subsystems within a 6DOF simulator to evaluate the antenna design's performance for system-level objectives, which is our final key feature. By leveraging these 4 key features, we are able to perform design studies which incorporate the effects of hypersonic environments on the seeker performance in a computationally accelerated timescale. The Hypersonic Digital Engineering Testbed for evaluating concept radars is a unique radar seeker design environment, which captures the aerothermal, thermoelastic, and electromagnetic multiphysics of the hypersonic environment to perform design trade-offs. Our goal is to work with the Navy and broader DoD hypersonic programs to support seeker design and analysis of alternatives. To support these programs, we will work with our Navy collaborators to define the desired design performance objectives and constraints. Using this information, we can then automate high-throughput design studies. Towards transition is to continue verification efforts of the integrated tool. Access to additional flight and onboard sensor data is critical to this effort. As ongoing verification is performed, we also intend to release a prototype version for beta testing. I encourage you to reach out to our team if you are interested in participating as a beta tester. Following the updates performed from the beta testing feedback, we will seek to begin transitioning the software to the Navy and broader DoD programs. We will also seek opportunities to collaborate with seeker design and system integrator primes. Thank you for your interest in our hypersonic digital engineering testbed for evaluating concept radars. If you have any questions or are interested in possible collaborations, please reach out to me, Andrew Kaminsky, or Vincent Harand, our Vice President of Commercialization. Our contact information is included here. Thank you for your time, and I hope to see you at our booth.